Oh, hey, Dr. Zhang, I didn't see you there. I was just in the middle of my heat transfer. You want to watch my heat transfer project? Let me tell you a little bit about it. So, it's pretty simple. I got a tube under this piece of metal right here. The metal is to keep the heat in. I have a burner under the tube, and I'm running water through it, and we're going to heat up the tube, and we're going to see how much convection power this water does. This is going to be some turbulent flow. Reynolds number is going to be pretty high, so Alright, so here we have a bit of water that is going to be the water going into the pipe. I have the pipe heating up right now, so we can't get that. So I'm going to test the temperature of this water. And the temperature is about 60 degrees Fahrenheit. So that'll be our initial temperature coming in, and then whenever we get the water running, we can get our temperature coming out. It is nice and heated up, and we got 3 more things to measure. We need to measure the volumetric flow rate, we need to measure the temperature of this water, and we need to measure the temperature of the wall inside that tube. It's going to be harder than it sounds, but we'll see if we can do it. So on camera, I'll do the temperature of this water right here. So this is after it's getting heated up. I don't expect too big of a difference, but we'll see. The temperature is actually 68 degrees, a pretty big change. So I went ahead and timed the volumetric flow rate and found that it was about 1.599 times 10 raised to the negative 4th meters cubed per second. The tube is about 20 inches long, and its diameter is a half an inch. So we'll convert that to meters. And I was unable to find the temperature of the wall, so we're going to go ahead and solve that algebraically, because we have a constant Q, the burner. That's a constant heat source that's putting in, so we know that Q is not changing. All right, so let's look at the Reynolds number here. So I was able to find the speed from the flow rate, and our Reynolds number is actually greater than 3,000. So this is a turbulent flow. And since our L over D value is between 10 and 200, I went ahead and chose the Nusselt number equation for a developing turbulent flow, which is equation 6.6 in the textbook. So for that, you have to find the properties of the bulk temperature, which is average bulk temperature is 17.8 degrees Celsius. So I went ahead, found all that, found the H to be 6,236 watts per meter squared times Celsius, and so we plug everything in. Our change in the energy of the change in temperature is equal to the convection heat that is done. So we solve all that. We find out that TW is 41.03 degrees Celsius. So our T wall is 105 degrees Fahrenheit, which is totally believable. I could probably put my finger in there and feel it, because the water has an amazing ability to cool that down really quickly. So here's the project. I had a lot of fun doing it, a lot of trial and error, but it was a good time. So this is a great last project, and hope I have you again, Dr. Zhang. See you later.